Slowly and back to work. Silence me, please.
Okay, you review your order will take by
And happy. 5 minutes. You gotta be kidding me. Hi, Charlotte. What's wrong with you? It says it's gonna be 5 minutes, but it's been 9 minutes now.
Maybe it just feel longer because you are in a rush.
I don't believe so. I've been here multiple times and it's been like this all the time.
So you saying the actual average waiting time might be more than 5 minutes.
Well, if that's true, that means the cafe's been lying to their customer.
Or maybe it's not just my perception.
Maybe if we can prove it.
How? With data. What are you doing?
I'm collecting data. I select every fifth customer and I record their waiting time. All right, let's start the timer now.
N equals 150.
Why 150?
The mean is calculated by summing all data and dividing by the number of samples. X bar equals to sum of all values divided by n. In our case, we collected waiting time from 150 customers. For this simple example, if we have 5 values, 9, 8, 9.5, 7.5, and 8.5 minutes, we add them together and divided by 5. The result is a mean of 8.5 minutes. And when using all 150 samples, the mean is also 8.5 minutes. We also need to see how spread out the data is, so we use standard deviation. First, subtract the mean from each value. 8 minus 8.5 equals negative 0.5. Square the result. Negative 0.5 squared equals 0.25. Repeat this for all values and sum them. Then divide by n minus 1 and take the square root. From the sample data, we get approximately 0.79 minutes. But using the full data set of 150, the standard deviation is about 2.5 minutes.
Okay, now I see. But this only 5 days of data, right?
Oh, yes, it doesn't capture weekends and seasonal effects.
So what does the data tell us?
Now, it's time for the hypothesis.
What hypothesis?
We test whether the true average waiting time is greater than 5 minutes. We use the z-test. By formula, z equal x bar minus mean divided by s divided by square n.
What does that mean?
We compare our sample mean with the claimed value, adjusted for variability and sample size. Z is about 17.15.
That's very large.
Yes, and we compare it with the critical value. Since we are testing whether the waiting time is greater than 5 minutes, this is a right-tailed test. We set the significant level at 0.05, which means we allow only 5% chance of it being wrong. So we're looking for a value where only 5% lies on the right side. This is the same as saying 95% is on the left side. From the standard normal distribution, the value that corresponds to the 95% is approximately 1.645.
So what's the conclusion?
Since 17.15 is much greater than 1.645, we reject the null hypothesis. The waiting time is significantly greater than 5 minutes.
So the 5 minutes claim.
It's not statistically true.
What else can we learn besides hypothesis testing?
We can estimate a range from the true mean. This is called a confidence interval.
What does that mean?
It's a range where the true mean is likely to fall. By formula, the sample mean of 8.5 minutes, standard deviation of 2.5, and sample size of 150. For 95% confidence and Z is 1.96. Next, we calculate the standard error, which is the standard deviation divided by the square root of the sample size. So 2.5 divided by the square root of 150 gives approximately a 0.204. Then we multiply by the Z value, 1.96, which gives us about 0.4. Finally, we add and subtract this from the mean. So 8.5 plus or minus 0.4. This gives us an interval from 8.1 to 8.9 minutes. This means we are 95% confident that the true average waiting time lies within the range.
So, what should this cafe do?
The cafe should increase staff during peak hours or improve their queuing management system. Because the problem is not just about the perception, it's about data.